welcome today. Today we'll be in English. Just a brief introduction, probably only for online guests. Ondřej Mottl is a member of the CTS, paleoecologist. He uses quantitative methods, advanced statistics, data-driven analysis, and so on. And for today, he prepared for us the talk called Window to the Past. Before I see what to speak. Okay.
Hello, sorry. I was sick over the weekend, so I'm wearing mask. I hope you will understand everything fine. Okay, I like to start my presentation with big numbers. This is a study from 2008 where they estimated that humans have altered more than 3/4 of all ice-free land, which to me is a pretty staggering number. And if you want to look into what we as humans have changed, then it's a pretty good idea to find out what the current state of the world is. So lots of people do big biodiversity pattern, as we discussed previously in the CTS. Biodiversity measurement is one way of measuring what's currently going on. So I like this study. It's from Patrick from 2019, where they look at the general patterns of trees, and this is tree richness. How many trees are there, either in polygons or in this is some model smooth. I think you can see there's a lot of trees, a lot of tree species in Asia. But if you want to compare what the biodiversity is now to what was it previously, you need a time scale, right? You need what are the biodiversity patterns across temporal scale. So we can see what was the changes in the biodiversity from before humans to humans, right? There are some studies who looked into this, how much biodiversity changed in time. This is a really cool study from Jordalas et al. 2014, where they look at a lot of data and their time sequences. And as you can see, they did like this, I think it's a ship, and they gather water and look how many planktons and other animals are there. And then they repeat this for many years. So they have actually quite a lot of individual records, and they look at the beta diversity, meaning the differences in species composition in this time. And indeed, they found out that over the years, we increase beta diversity, meaning that there is a bigger change. The change are more and more different than they were. But if you look at here, which is the scale, they look only, because this is current ecological studies, which are mostly limited to, let's say, last 100 years. We don't have that much data older than that. So the question, I think, good question is, what are the biodiversity patterns at larger temporal scale, if you go more into the past? And to put it a little bit in the frame, this is a figure from Kaufman et al. 2020. This is a temperature, estimation of temperature for the last 12,000 years model. And obviously, for the, I will a little bit guide you through, there's this big increase of temperature from last ice age, when the world heated up a lot, the glacier, retracted, etc. And then we have this relatively stable period, which we call Holocene. And then, of course, we have this increase in recent years, which is caused by humans. So we have the LGM transition, and we have the anthropogenetic changes, right? This is increase. And I think the good question is, we can compare how much these changes caused by humans are related to the biggest change we know to this recent, period, which is this heating up of the world. So I don't have to. I hope I have to introduce myself. So my name is Ondřej Mottl. I'm currently assistant professor at Charles University. Also, on top of, I'm also a member of the CTS here. Through the presentation, there will be QR codes. I'm aware that for those who are not so skilled, there are also mostly the links written here. So these are, for example, this will get you to my personal website. And this is how to reach out to me. Okay. So through the presentation, I will be talking about ecosystems and biomes. I will be also talking about lakes and deposits. I'll be also talking about stats and data science. I'll try to keep it to minimal, but since it's my expertise, I can't promise. And I'll be also talking about prehistory humans, right? So kind of the topic for this presentation, what these things have in common. And hopefully after this presentation, you will know. So the title of my presentation is Window to the Past, and it's mostly focusing on paleoecology, which I know there are people who have been doing paleoecology, but for those who don't know, I will kind of refresh your mind how this all works. So in order to do this window to the past, to look to the very old past, we need two things. We need sediments. This is an example of sedimentation, right? And we need pollen, especially pollen grains. So we probably know, especially in the hay season, for those who are allergic, this is a pollen grains. And if you look under the microscope, you can actually, some people can actually identify these pollen grains to, let's say, species or genus or family, right? From pollen grains, you are more or less able to determine what was the plant. And if you have these two, then what actually is happening? So this is AI generated, so take it with a pinch of salt. So the trees will produce some pollen grains. They're here and they fly and they deposit on the water. And they will be in the water and then they will sink down to the bottom and create a layer, right? So all the trees around the lake will produce the pollen and then will create a layer. And if you wait 100 years, there will be a different pollen grains flying around and they will again put it to the water, sink down and create a new layer on top of that, right? And you will have this slowly accumulation of layers, including these pollen grains. So fossil pollen is a great source of information because what you can do, you can find a lake and what is called core it, meaning someone will stick a huge, like a cylinder to the bottom and take out the sediment, and these are the individual layers, right, which you can find. So by the way, this visualization has been done by Milan. She's my really good friend. Follow her, she's really good. So then you can look into these individual layers, and some very skilled pollinologists are able to count the individual pollen grains and identify them to species, genus, family as well as they can. And then because you have the information about the composition or relative abundance of the pollens, you can kind of reconstruct what was the vegetation history of that place, because this goes in time. And if you have reconstruction vegetation history, you can say something about the ecosystem, right? Hopefully. So I included also these figures, which I think are beautiful. This is done by Jill Pelto. She's a really talented paleoecologist, but also she's doing these amazing drawings. So this example of visualization of the layers, various things in them. This is a nice figure of how the coring is actually happening with the cylinder. And this is actually a visualization of what is quite often how these lakes are cored. Because in order to get to the center of the lake or to a good place, it's much easier to wait until the lake is frozen and walk on the ice and then drill to the bottom, right? So this is how it's actually quite often happening. And I have some other pictures how the sampling of these cores is happening. So there are various methods going from, as you see, these like ice cores where they dig a hole in an ice lake and drill to the bottom. Then there is this rafts where they actually have a boat and go to the middle of the lake and core. But you don't have to do it with lakes. You can do it also with other like watery sediments. So it could be marshes or mires or swamps in general. But also there are these huge, where is the picture? There are these huge offshore big drilling things or big ships who are doing this, and these are marine cores which are very deep. And this is all other things. So there are just some examples how this is happening. And the people who will drill the cores and count the pollen and then assign them to different taxa nowadays are very, very, very helpful, because what they will do, they will share it to an open access databases. The biggest one is Neotoma. And the Neotoma currently have over 6,000 individual fossil pollen data sets, meaning there's this over 6,000 cores who someone actually look into, drill, count, etc. So this is actually a really good source for something which I like to do, and is to look from big data into some patterns which we can tell about, let's say, ecosystems. So, but if you want to do so, if you want to dig into this big data set, you need to, have tools which are reducing the bias by use, because you can imagine different people have taken out the cores, they use different methodology, they were different skills, etc. And also there are differences in the depositional environment. Some use mires, some use lakes. There might be differences. I need to kind of need to take care of that. So in my work, which I've done previously in Bergen, Norway, I was part of the project called HOPE, Human on Planet Earth, which I will talk a little bit later, which was 5 years ERC project given to Professor John Brooks, who is excellent pollinologist. And there I developed a tool to do this in lots for you. So if you have, this is a little bit technical, but I think it's interesting. So if you have data set compilation, right, and you know there are various things which are affecting your data, right? It could be the sourcing. Are you taking just from the one database? Are you taking from multiple databases? There could be differences. The depositional environments themselves. Are you using just lakes? Are you using mires? Are you using the ocean drills, right? There could be very different stories going from the lakes and from oceans. How have you built your chronology? That's a very technical thing. And then filtering, meaning what data do you want to keep based on your criteria, right? So because this is kind of complicated thing for other people, I built what is called Possible, which is a tool for other people to use. And it's a workflow which should help the users to gain the most of the data they want for their specific project. I will not go into the details. Oh, this is not very well seen. So basically, the user can specify what are their research questions, what they want to know. Let's say, what are the biodiversity patterns in pollen across Europe for the last 12,000 years? And this program will guide you through it. I will skip because this is very technical and help you to find, for example, it will say, I want to have it for Europe. It will say, okay, go to the next step. And next step, it will ask you, hey, in your current assembly, I found you have all these depositional environments. Which of these do you want to choose? Which of these fits your question, like research question? And you pick which one you use, and then it will go next step. It will rerun all chronologies using the modern statistical method. It will harmonize with pollen grains, which I think is important, and I will talk about it. So you can imagine if two different people have two different data sets and they try to identify pollen grains, depending on the skill of the pollinologist who's doing the identification, depending on the microscope, depending on the reference collection, they may be not able to do the same classification, right? Or some people may find out that they will put, I would say, creative names for a various things, right? So some people may say, this is Quercus. Some will say, this is Quercus type. And some people will say, I'm able to determine which of these Quercus it is, right? But if you then want to compare these two cores, statistically, this is very difficult because you will find out that there are different taxa, even though we know they are probably the same taxa. So you need to do a step which is called harmonization, meaning to put everything to the same taxonomical level and synchronize the names. And then there's also critical selection where you say quality of your data, how many samples, etc. you wanna. And in the end, you have the data set compilation. You will have all pollen diagrams, which are really important for pollinology, because you can look at the vegetation history. You will have age models and some graphical visualization of your data. And what I think is really important, I'm very proud, you will have citation metadata, which is a file which you can share with your paper, and that will it will include all the settings and all the files needed to reproduce your exact selection of the data. So if anyone else wants to repeat exactly what you've done in your study, you can just share that one file and say, I use Possible version 1, and this is the citation metadata, and they will be able to reproduce exactly the same. On top of that, it also includes a link to the individual data sets and who are the owner of the data set, who put the data to Neotoma, and you have a list of all your people who contribute to the data for your specific project. And it's up to you. Do you want to invite them as co-author? Do you want to acknowledge them at least, etc. Right? Because we understand none of this would be possible if people are not willing to share the data. So I thought it's very important to make sure that they are somehow acknowledged. Okay. So this Possible, it handles all the steps and flags which user needs to do this compilation. And this all has been published in a paper, Guide to Processing and Standardization of Global Polyecological Data in Global Ecologic Biogeography this year with me as a joint first author, which I'm very happy. And we also launched a website. So this is how the paper looks like. And again, sorry, these are links, but if you just find Possible, we have websites where there's all the technical things you need to do for step-by-step, how to report bugs if there are any, etc. And this is the paper, and these are the project. Okay. And some examples how this works. So as I talked about the Scandinavia, this is actually example which is also presented in the paper and on the websites everywhere. So we thought, we take an example of, imagine you want to do a biodiversity study, how much diversity changed in Scandinavia for the last 8,000 years. That's an interesting question. And it will start with this selection of which you divide, said, this is where it's Scandinavia, let's say. It will get over 300 data sets. and then you will go step by step where you select your criteria, which I selected personally, and then in the end, you will have 113 datasets which are suitable for your questions. And even though it looks that you're losing a lot of data, our argument is that your quality of the data which you need to answer your questions is increasing drastically. Because you don't want to use garbage data which doesn't bring anything to your research question. You want to use data which are relevant and have the quality you choose to keep, right? And then, so this is also automatically reported from the program. This is kind of spatial distribution of the individual records. So the points are the individual data sets. Then this is the number of data sets in spatial delimitation. Here I choose the WWF biome. So we have 50 in temperate, broadleaf, and mixed forest, which are current biomes. And then this one is actually the temporal visualization of all the records, where each small line is one record, is one data set. And you can see I selected that the data set should covering, between 0 and 8,000. So that was my window of interest. And that's why all of them are more or less in this way. Okay, another example which I want to show is another project which I'm working on, which is a Latin American synthesis, where we are looking into synthesizing, some new information about ecosystems over the whole Latin America. And in this project, we use, of course, fossil, but we also reach out to local scientists who have done data, who have their data on paleontology and included them in. And this is now built in the fossil. You can use both Neothelma, which is the big database, but also your own data if it's not in the database, and it works the same. So it's a huge achievement. You can see half of the data we are using is actually not in the database yet, but we are trying to help them to upload it there. And then the reason why I'm showing this is going back to the harmonization. And so this is the number of taxa presented in the data. So the red one is if we would just take the names as they are from the authors, and the blue one is the harmonized one. So you can see this is 4,500 or something, and this is over 1,000, 1,500. So we lose lots of taxa, but that's not the case. It was just quite a lot of various, variation of the same name over again. And we just put them to the same thing. And if you look at the number of taxa per dataset, per record, that didn't change almost at all. Because what was important, you need to compare apples to apples and not apples to oranges. And this is a paper which is in a very advanced state. I can't show the result at this end. Okay. Speaking about the harmonization, this year we also published a paper which is going more into detail how this is done and everything you need to know in a review in Paleobotany and Palynology with John Burks. And on top of that, in the supplementary material, we included harmonization tables for all continents but Africa. So if you are doing a big scale thing, you can go to this paper, download the harmonization, and adjust it if you need it. But this was a big work which we've done. It was also published this year. Yeah, you can see it's in the future, December 2023, which I really like. Okay, so that was not about the data. Now let's go to the ecosystems themselves, right? So I really like this concept of planetary boundaries, which is also the name of a new working group from Pages, which some of you may know, which is Past Global Changes, which is a great initiative. And what they are saying is, this built on this Stefan et al. 2018 idea that here we have time on this axis, we have stability, and the color is temperature. So we know that the Earth was, going between glacial and interglacial cycles, and then at some states, which we are here, it seems that it's going to this hothouse Earth, where it will be very hot, it will be very unstable, etc. So what we as humans want to kind of do is to stewardship, to steer it a little bit to what's called stabilized Earth. It's not going to be perfect, but hopefully it's going to be better. But if we don't know the long-term data, we are trying to return it to unknown condition because we don't know what the condition actually looks like, right? So we need to look for the drivers that cause this transition between, going to stabilized or hothouse. We need drivers who's doing this. And therefore, we need to define ecosystem properties. So we need to define variables which will help us define the current state of the ecosystems, right? So we need to describe them somehow, hopefully statistically. This is what I'm doing. So in this framework, So the planetary boundaries working group has their first, it's very young group. We have our first meeting now in July in INQA, which is a huge conference in Rome. Okay. So these ecosystem properties, going back to this figure, you have the leg, you have the pollen, you have the vegetation history, and now we want to say something about the ecosystem. So in order to do so, to help doing so, I created another tool which should help you define statistical variables which are used to describing the state of something. Well, it's called ecopol, or r-ecopol, it's our package again. So it's basically just the user-friendly wrapper for lots of statistical functions to make the people, do that easily. And there's some diversity estimation, taxonomic functional phylogenetic diversity. There's some ordination, including DCCA, which to my knowledge was not present in our environment before. Some temporal trend modeling, like fitting, predicting, visualizing higher accounts, and some other stats things. So this is what I've been working on. This is kind of tool for other people to help them, look, because diversity is a good example of how you can describe easily an ecosystem, right? So I thought, oh, we need to help other people use it, specifically for fossil pollen data, to create these estimates. And this is actually exactly what we've done. So this is another study where we look at Asia, because Asia is huge. What is interesting about Asia, it's spanning quite a lot of these climate zones, which are the colors in this on this map. The background colors are the individual climate zone from Copenhagen. And the blue points are the individual records. So we have over 200 data sets again. And then we try to describe some patterns in Asia, right? So I'll try to guide you through. It's a little bit complicated. So we have some diversity, meaning how many species are there, right? That's a good example how to describe ecosystem. We have some evenness of the community, which is some the ratios of the diversity. And then we have some turnover, how much change do we see in the composition? And we use first axis of DCCA and rate of change. And then we looked at 3 different spatial scales. So we look at individual records, meaning these tiny lines, I'm not sure if you can even see, but these tiny lines are the individual records. Then we built a bigger model, which included lots of data from across whole climate zone. And these are these lines. And then we built one model for the specific variable for the whole continent. And as you can see, there is not much else which makes sense. It's just all random, there's huge variability. But if we do not look at the trends themselves, but if you look at the change point, meaning we are interested, it doesn't matter if the diversity goes up, if there are more species or less species suddenly, what is interesting is the change, right? Suddenly something happened, it caused increase or decrease, so we look at we derive change points, we call them change pointing strengths, and we look at the density of those change points, right? Are there time periods where there are more change points at the same time scale? And if we look at that, yes, indeed, around 8,000 years, something happened in Asia, which caused lots of different of these estimates to change, either up or down. And it is pretty complex study. So if you want to read it, it was published this year in the Frontiers in Ecology and Evolution, and with first author of Kubabata. It's a mess, but I think it's interesting that the fact that it's not, you need to think about what you're actually looking at if you want to describe this ecosystem. Is not just very simple to just, I want to look if the diversity is synchronously going up or down. Maybe sometimes it's better to just look, are they actually changing? Okay. And then the last point, which I want to say is, for those, I'm not sure how you know, but these are functional traits. So you can imagine maybe the species diversity is not so important for the ecosystem. What is more important is these niches. So we know there's a big tree with big seeds, and that fish, that fits one niche, and there could be other niches. And to do this, lots of people currently in ecology use what's called functional traits. There is this paper published in 2016 by Diaz et al., and they found out there are 6 functional traits in plants, which are very good at describing general, describing the ecosystem, right? So it's the height of a plant, is the seed mass, the nitrogen, it's the nitrogen mass, is the leaf area, is the specific leaf area, etc. There are 6 of them, and we thought, this is very interesting. It would be cool if we can use the same framework and use it for the fossil pollen data. But of course, there are some obstacles, so we found out. So we created this kind of scheme how to do it, which is maybe even too complicated for now. I just want to say that we did a review also published this year in Functional Ecology, where we explain or suggest a way how to efficiently use framework of these functional traits to fossil pollen data, and basically that means lots of linking taxonomic data, etc. Okay, that was a segue, and now the next part, which I'm going to be talking, I'm going to be talking rate of vegetation change, because that's the topic I've been, specialized in for the last few years. And yeah, okay. So this is one of the ecosystem property which you can tell to describe ecosystem is rate of vegetation change, right? But it's kind of difficult to imagine what the rate of vegetation change looks like in an ecosystem. So I have this visualization. So there's a time on this axis, and this is an ecosystem. And you can see with time, each time step, not much change in the terms of species composition. You see there are more or less the same trees, right? There's a little bit of change and then nothing. There's another ecosystem with each time step we see more species changing, right? Sometimes it's turning into a bush, etc. And then with this last one, basically with each time step we see that there's completely different ecosystems, right? There are completely different species, etc. So you can say that these three have different rate of vegetation change because the top one is changing the fastest. And again, this artwork is done by Milan, my really good friend. She's super talented. Okay, so we now know what does it mean rate of vegetation change. And in order to estimate it, it was a little bit difficult for possible data because there's a lot of uncertainties, especially around the ages. So I created another package which is called R-Rainfall. I'll just quickly go through. It has some novel moving window approach to this. It considers age uncertainties, taxa standardization, and peak point detection. So, because if you think about it, if there is a rate of change in the ecosystem and suddenly the rate of change increased because something changed quickly, right? It was humans, it was changing climate, but the composition responded quite quickly, then these are the periods we are very interested in, right? So I created just simple algorithm which will look for these sudden increases of rate of change. I call them peak points, and this is relevant later. So this is all, again, publicly available. There is a paper published in 2021. It means the first author about it. Okay. And then what we've done, we use the package to determine the rate of vegetation change on the globe. And I was very, very, very happy and lucky that thanks to a great team of people, I was able to publish this as first author in Science. So it's called Global Acceleration Rate of Vegetation Change over the last 1800 years. So if you haven't read the paper, I recommend. I think it's a good paper. Okay, so what we've done, we've taken lots of data from Neotoma, right, which was a mess. Then we apply some criteria to make it a less mess, and then do some data modeling. It's not important, but it's important. This can be now replaced with this first package I created. It's simple. Then you need to estimate the rate of change for all these individual cores. This is done by the second package. And then you need to summarize the patterns across various scales. And this can be now done with this third package. So this is how you can see how these packages are kind of nicely hopefully linked together. Okay. Okay, so what have we actually done? So this is the distribution of the data. We have over 1,100 records, which was at that time there was the maximum which fulfilled the qualities in 2020, right? So a few years ago. Nowadays it's much better, especially in terms of Latin America and Oceania. There are much more data actually. And to put it in perspective, there is this Stephens et al. 2019 estimation, which they say that around 4,000 years ago, the intensive agriculture became relatively widespread, right? This was a famous study, which I think is really important for putting this to the setting, right? We also have the temperature for the last 18,000 years, the CO2, etc. What is also important is this distribution of how much data do we have. And this is the box plot or violin plot, and you can see we are relatively good about the data. And then around 16,000 years, the amount of data started to be less and less. That's why we decided we cut it at 80,000 years. We didn't go more back, even though it would be interesting, but we just thought we don't have enough data. Okay, this is the result of the study, which is a terrible picture for presentations. So, but it's a cool, so in general, as you know, pictures to papers are great for papers, but not good for presentations. So I thought I would break it down to make it more sense of this. So we have 6 continents. Right? It's North America, Europe, Asia, Latin America, Africa, and Oceania. And then for these all, we estimated the rate of change for these over 1,000 data sets. And then for each continent, we summarize them over 500 time slots. And these are the individual points. These are the summary values of the rate of change for individual for all continents. Then we fit some general additive model to make it like a trend. And then here you can already see the first result, which is this increase. So these are rate of change values, right? How quick things are changing. And you can see here, this is, let's say 3,000 to 4,000 years, we see that things start increasing, meaning that the vegetation or ecosystems are starting changing more and more quickly. And then what we look also was, what was the highest value of rate of change since the last ice age, which we know was a huge, right? Was a huge increase of temperature, the glaciers went away, there was lots of new vegetation changing. So we want to compare how big differences are today to the biggest differences we see since the last ice age. And actually, this is another result. So the changes we are seeing today are as fast, but mostly faster than anything we see since the last ice age. And then we look at another thing, we call it synchronicity. But basically, what does it mean? It's we look at these peak points, if you remember. So these are the periods of sudden increases, and we look how many data within the continent have these peak points at the same time. So higher these values, that means that more records are behaving same. The data are doing the same, they are samely increasing the rate of change. And again, we fit some model, and then we found out the same, right? Not only things are the rate of change is increasing, also more data sets, so in more places within the continent, we see the same thing. So they are going more synchronously up. So we then have the curve for rate of change, we have the curve for synchronicity, and then there's a statistic, but we look for first derivative of the function, meaning where statistically we see either increase or decrease again of this. You can imagine remember the change points. And whenever it is changed, so these are the black asterisks or point, and we can roughly see, which I think is interesting, is 3,000 to 4,000 years, things beginning already to increase up, right? Going both rate of change and also the synchronicity. So this is the figure.
The situation in Europe is probably the most dramatic. So how is it? Do we know something about it?
So this is all study because it was published so, I would say almost 3 years ago. The main goal was not to attribute these changes, right? We were just looking, no one else looked at this at all. We want to just produce some information about what was happening. We were especially very, very, very careful to say this is not humans, right? Because we didn't have the data to support it. Of course, we know the Stevens paper, which I think is relevant, which we know around 4,000 years, the intensive agriculture became widespread. That's what they say. Yeah, so it kind of aligned nicely, but we can at that time we cannot say anything about the causes. Of course, we suggest these is the climate, this is the changing of the temperature on the globe and also other things. And then we suggest these are human, right? But we don't know because we don't have, at that time we didn't have the data. Okay, we also redo the analysis on subcontinental scale to look at some small patterns, and we find out similar things. We find out that, of course, tropics are much more, there's much more variability in tropics. The things are going a little bit crazy. And the main message is, I'll try to summarize it. So the rate of vegetation change are now as fast or faster than I think we see since the last ice age. We see that surprisingly, this increase already, started 3,000 to 4,000 years ago. And so if you remember in the beginning of the presentation, I was showing that in this 100-year study, they found out that indeed the beta diversity is changing. All these studies we're doing with the modern ecology, this is probably just the tip of the iceberg of things which start happening already, a few thousand years ago. So, and I have to stress again, this was the first quantitative detection analysis. That's why it's broad strokes, right? We don't go into much fine details because we were just interested in what is the big picture, right? Because no one knows about this at all. And it's only possible through lots of community of biologists who are willing to share their data, and then a huge team of people working on this paper who also made this possible. Okay. So I think that's also nice a conversation topic to the question, what is pristine, right? Because you can imagine if there are lots of conservation efforts to rewild the nature or put it to their natural state. But if we know the things potentially you can start changing it 3,000 years ago, I think it's a good question to ask to what state are we trying to restore it into, what is actually pristine, etc. So this is maybe later for discussion. Okay. So as you can see, I really like making tools for other people to help them scientific exploration, right? To find something new about the world through software, because I think I'm decently good at this. Okay. And next part, which I think is very relevant for CTS especially, is the human impact, right? Because as you see in the study, we were not able to tell if it was caused by humans or by climate, this recent increase. So we looked into ways how we can actually determine if there is a human impact in the data. So I really like this paper from, I'm butchering the name, I think Kauri, but I don't know the pronunciation, from 2016. And this is super nice visualization, and basically they did the review of all plants which are human associated. So these are plants who people plan to eat, blah, 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 etc. on the world, which I think is super nice visualization. But you can do something similar with the pollen grains, because you know there are pollen grains, let's say, of cerealia, right? Which is cereals. And you can imagine if there are lots of pollen suddenly of cereals, that there was probably humans who started planting them around. So there's this idea to use pollen indicators as indicators of human impact, right? Lots of them are Plantago, and there are quite of them in Europe, and they differ across the world. And this is a recent publication by my really, really good friend Susan Plantua in Scientific Data, like a month ago, where they actually go and look and do a huge review of all different possible human indicators in Latin America. And as you can see, these tiny things are the individual indicators. That's not important what they are, but most of what is important, they are mostly very, very, very rare. Right? So these are rare taxa, which can be used for food or for dyes, clothing, etc. So they are rarely there, but if they are, we can use them as a source. Oh, potentially humans are also there. And linked to that, there is a student called Midori I'm working with, and together we are doing this. We're focusing on Northern Andes because that's an interesting part of Latin America. And this is a little bit technical, but we are looking basically if we are able to, across these Northern Andes, to find similarities within the presence of different human indicators. Right, that's kind of summary. So these are individual cores, meaning sequences. The colors represent Venezuela, Colombia, Adrian Valley, and Ecuador. Right, these are the color things. They're ordered by latitude. And this is time scale, right? So if all things came from empty to full at some time, that would be a good indicator that that's the case. This is kind of a summary. We don't find it. We found out it's much more difficult, different and difficult. And this is going to be generally quite often how it is. So these pollen indicators are very local, and the effect you can find is very scattered across and will be very localized, right? And that's kind of a summary. So, but this is work in progress. But amazing thing happened in between, that there is archaeologists have been dating their artifacts, right? And you can imagine it could be an iron sword, or it could be a pottery, it could be whatever. And if you radiocarbon date it, you will find out how old it is. And actually in 2020, my really good friend Darcy Bird published a paper, again, I think it's Nature Scientific Data, and they published a database with all these artifacts. Right, so theoretically, this is what the archaeologists doing, is you can imagine the more artifacts you find, which are the same age, you can imagine that kind of proxy how many humans have been there. It's a huge estimation, but this is what quantitative archaeologists have been doing. So immediately, that to me was, this is great, this is independent source of the human presence of the humans, which we can use to detect if indeed they have impact on the ecosystem, yes or no. So this goes back to the project I was talking about, human on planet Earth, which is one simple question, which is very difficult to do, which is, did the prehistoric humans alter these ecological properties, right, these ecosystems, in the last 10,000 years? And what we've been doing in this paper, where I'm joint first author with Vivian Felde and also Sue Plantua, where we can test this, right, because we do have the data. So we have the vegetation data from fossil pollens, right? We have the ecosystem properties, which we can describe what the ecosystem looks like and how they change in time. Then we need to somehow estimate the human impact, how many humans were there, or how big impact it was. And it can be done by human artifacts from the radiocarbon dates, all these pollen indicators, right? And then we will compare it to climate to tell, was it more humans or was it more climate to actually change these ecosystems? So this is in the works. I sadly legally cannot show you more, but this is very exciting, hopefully. And it's something I've been working on for a very long time. Okay. And the last section which I want to talk is what I'm actually doing here at the CTS right now, and that's called Project Biodynamics. So I have been awarded by the Czech Science Foundation my personal lecture, and the project is called Biodynamics, the spatial temporal dynamics of interaction, where I'm the PI, and the only employee also, obviously. So the project is looking at, again, a global biodiversity pattern of vegetation, because this is what I like to do, and this is my expertise. But specifically, I will be looking at non-random occurrences, meaning I will look if taxa occupy the same space more randomly, less than random than we would expect, right? For example, you can imagine that if there is an open landscape and suddenly there is a new tree coming and the tree grows, it will create a shade for other species that suddenly can grow there also, right? So these two species are non-randomly occupying the same space because there's some biotic interaction together. This is a very problematic terms in ecology because lots of people will not call this biotic interaction, but that's just, I think, taxonomical thing, right? You can just call it that. So the project is very interdisciplinary because I will be using neo-ecological data, paleoecological data, some community ecology matrices, functional ecology using the traits, eco-informatics, etc. So what is cool about the project, I will look at 3 different scales. So I will look at spatial scale, meaning from a very local effect to the whole continents, how this changes if you look at different scales, because we know this is important in ecology. I will look at temporal, because we know that the changes in biodiversity observing right now probably began 2,000 years ago, so it's important to have the time frame. So that's why I'm using paleo data. And I also look at taxonomy scale. I will look at individual taxa. I will also look at then genuses and families, if the patterns change, if I go more abstract. And then finally, I will do completely abstract, where I will not use the taxa themselves, but I will put functional groups. So I will group the taxa into groups. It's a big tree with broad leaves, or it's a small herb, right? And I will use these instead of the taxa themselves to look at their concurrences. So what I'm doing right now, I'm actually, to do so, you need a lot of data to answer these questions, right? That's very data heavy. So I'm actually building what I call VegVault, which is Vegetation Vault, which is open access SQL database with vegetation plot data, global plot data from current ecological data like splot and BN, and also including the fossil pollen records. So taxonomy classification for all taxa present there, meaning I can quickly summarize the data on whatever scale or genus or family, etc. I will have the traits, these functional traits I mentioned from the DIAs, these 6 ones. And also abiotic data like climate, soil patterns. So for technical wizards, this is my visualization of my SQL database, which is not so important for the people, but the important thing is this is happening and I'm actually making it, which I'm very happy about. And this, I created a website directed to this project, my current project, which is Biodynamics. You can find it easily if you want to know more. So I hopefully talked about ecosystems. I talked about lakes in deposition environments. I talked about some stats, and I talked about prehistoric humans. So hopefully there are some connections between these for now, but I really don't like Steve Jobs, but I like this quote. And I think this is cool because this is really true for my personal career, is you can't connect dots backwards, forwards, you can only connect them backwards. I would never guess, when I was finishing my PhD in tropical ants, that one day I will be here presenting about prehistoric humans and global biodiversity patterns. So in general, if you want to get, participate in any of these projects, get touch with me. I'm very happy to collaborate. And this is not here relevant, but I have now, if you know any students who may be interested in this, I have 2 open student positions at the Department of Ecology. Okay. I don't know what's the time.
Yeah, we have open to 11.
Right. 45 minutes, that was my aim, so I'm very happy. So hopefully this was understandable and I'm ready for discussion.
So again, we have plenty of time for this.
can you say more specifically how you think you can connect the idea of planetary boundaries, like whether the Earth is in a stable state with your ecosystem properties?
So we can't tell if it's in a stable state, but we can't derive or estimate variables how it was before, right? From the pollen, and you can use different, and the whole idea is we just need to find what the good matrices are, or the indices are. So it could be biodiversity on the taxa, it could be the rate of change, it could be these various things. We basically need somehow to describe how things were to be able to also describe them today and then compare, right? And how we will choose these, this is yet not unclear. How find out which are these who are important and how to do the steering is also very clear.
But like you must have some idea like how to define whether it's stable.
So what they want to do, or one of the ideas we propose, is basically to look at the temporal trend of these, and if they suddenly start again increasing or decreasing, that's a bad sign, right? So there will be like levels of, and I think this is, I haven't got a visualization, and this is what they propose. There's the planetary boundaries, which you kind of circle, and you will see how much change you see in these variables, and if they cross, certain threshold which is set up based on, let's say stats, then they will say, oh, careful warning, in this part of the world, something wrong is happening. You need to watch it out, right? So it's mostly about where do we put funds, let's say, nature conservation, or where do we even look at what is happening, right? So we need some kind of relatively easy, quick tools to estimate this. So that's kind of the whole idea. So it is, as I said, it's a very early thing, but basically we are looking into this pollen modeling, lots of how, and also, like temporal trends modeling, seeing if, let's say, diversity in somewhere is suddenly increasing or decreasing from the current ecology. And they're also looking quite a lot in satellite images and searches to use those as a data of what is happening right now. We have lots of data. So I'm not saying this is what is going to be used, but these are the options now part of the group is exploring.
So you just think that if it is changing too fast, it means that it's not stable.
Yes.
But it can just change fast because it's going towards stable state, for instance. So how do you like?
To be honest, I don't know. As I said, we are in a state of lots of discussion and workshops, etc. And these are the topics we have been discussing, and we didn't find any solution. So if you want to, join the group and also look in this, you're more than welcome.
I agree. Yes. Actually, the same or a question on the same topic. So, like the picture that you have shown, there's like you assume that a stable state exists. There's like local equilibrium, right? Like it may or may not exist. Like there could be like a stable path or something, or maybe there are only like two stable states, and so on. So like, what are your assumptions? Like, why do you believe that there is a stable state between like the cold and hot state or whatever? This one. And then the second question is that what I think is very important are the values that are behind this, right? Because planet probably will exist. The question is whether it will be with humans or without humans and so on. And I think your assumption is that like if we keep whatever it was in the past is good. If it changes from what it was in the past, it's probably bad, right? But maybe do you have like more explicit like discussions of the values that are involved and like?
Yeah, of course, and I think this is very nicely tied to the discussion we had in the CPS, and I think it was last Monday when we discussed how to describe, ecosystems in general, and of course, we are. I agree. The big assumption is that there is stable state, which we don't know. Maybe we are past the point of no return, right? That could be the case, but I think it's still worth trying. You know what I mean? At least, but of course and that's why we have this kind of interdisciplinary group that was similar to kind of CTS, where we discuss what are the good values, right, to choose from. And of course, there are plenty of them, and we will never know for sure, but we can try picking, right? We can try to derive, look at the data. Mostly lots of the things we're currently, the main, stats person is Alistair Saddam in this group currently. And he's not confident, but he is very optimistic about that. If we have enough data to describe the world, we should statistically be able to find some variables which are important, right? Because we will see, because it doesn't have to, because the fact that it's not what the whole thing is not, we will do something now, but this is continuous thing, right? We will set up a framework and we will continuously monitoring Earth and look at these variables, what they are doing. And hopefully we will be able to detect a period where careful, we are, getting close to this planetary threshold. Maybe we passed it, that's true, right? We never know. But yeah, but that's kind of the whole idea is hopefully we haven't passed it yet. And let's try to find out ways to steer it back. But if you don't know what back was, right, and that's kind of the whole promise of that, we can't steer it anymore. And we don't know, you're right now we don't know the direction we are actually heading, right? Because we don't know the back data, or we know, but not so greatly. And I think that is, I'm not saying this is, without an issues or without an error, but I just thought it's a very interesting thing to do, and I'm very happy to participate with any knowledge I have to do this, because I think it's interesting, and and I feel my expertise, I can provide something which they can't, right? So I'm very happy that they're very happy that, he's actually able to give us lots of data from the past. So yeah, I'm just like, okay, this is great. So the collaboration is very interesting, and I think that's what is important, right? I'm not saying this will be super successful, or we will change the world and we will have, documents on policies and this kind of thing. But I think me as a researcher, I thought it is good cause to join to do this, right? Because to my knowledge, I didn't know, or I haven't found anything else who would try to do something similar in my close networking that I joined. Of course, there are also people looking into this, but because I know some of the people there, I just found this is cool idea.
If I may very quickly follow up on this. So I completely agree. It's very important. So, but do you have any idea what does it mean to be in the hothouse Earth? Because okay, as I understand, you ultimately want to show, okay, if we don't do anything, we end up here. It has these consequences. If we do this, we end up here, and then it's up to some democratic processes, and people will decide what they want, right? And so, do you have any idea what will happen over there in the red, hole?
Of course, we don't know what will happen, no, but we can make assumptions. There are some models which show what would happen, right? If the temperatures start increasing, we know that there are lots of internal, self loops, the ocean, pH thing, and then we know it's not just one threshold. There are quite a lot of thresholds. We know, for example, if you cut a lot more of Amazon forest, we know because of the humidity and the clouds, it will have severe consequences, right? Of course, we don't know when this will actually happen, but we kind of know it will happen at some point. So hopefully this also will help us to find out more when this will happen, right? Hopefully to find out this is actually the state. And it could be, one of the variables is just from, satellite imagery, how much forest do we have, right? I'm not saying this is great, but it is thing to know, and to continuously observe this and observe the changes in this on a certain scale, to my knowledge, is not happening, right?
Predictions are extremely difficult, especially for the future.
Yeah, of course. I'm not saying it is easy or etc. But again, I'm saying I think this is a good cause. It makes sense to me to try to do something, and this is, I think, personally, I think this is worth putting my energy in. Right, that's what I told you. Yeah.
I'm still not sure if I understand. So, if the Earth is going towards Eocene, for instance, in terms of temperature, how can you use your data from the past to make it more stable? just to be maybe more specific, like how, like of course, ideal how to like switch the path would be to decrease the temperature, but like
or stop increasing it, right?
or stop increasing, but like but this is not like your project, so I'm asking like how your project based on the ecosystem properties, how it can actually help to
Okay, I'll try to
change the path.
Okay, no, we can't change the path, right? That's first of all. Second, this is not my project. This is a huge project. I'm just there. I just like the term ecosystem properties because it is true that we need to, in order to tell something about Earth or the changes we are observing Earth, and we do have now information about what's happening in Earth, but we need somehow to describe the changes, right? And then if basically, if you just know, oh, the Earth is getting, hotter, and for example, and we would not know how much different countries producing CO2, it will be, but we know that, and we know they're producing CO2, so we can create a policy who make sure that they reduce the production of CO2. Right, that's one example of the policy, of course, but we can.
Yeah, but I'm like asking about the ecosystem. Like,
yeah, exactly. I'm getting there. So you can also say that we know that, for example, in tropical forest, in Brazilian forest, there are changes happening, right, due to human activities, blah blah blah, and you can observe these changes, and you can also observe the changes in the past, how they were from relatively hot to cold, etc. How the ecosystem responded to these changing temperatures, right? What actually happened? Maybe we will find out that at certain temperatures, this cascade of changes will happen in the Pacific. We can use this information to say, oh, be careful, we need to be really worried. We can't, do this and that and that because this cascade may happen, right? So I think to me, this is just a framework to say we need more information about what is currently happening and what have been happening, right? Because without that, you can't do any prediction about what's going to happen if you don't have the past, if you have only the current.
But I think for this, we just have to increase the temporal scale, which is not possible because you need like the periods of like extremely high temperature, which did not occur still to our glacial maximum until now.
Yeah, but there was a period of increasing temperature, right? Well, yeah, it doesn't have to be the same temperature, maybe, and this is the work from Matthias Gergeiser, he's a PhD student in Bayreuth University, and this is what he actually has shown in his paper, that what is important is if there is long-term temperature increase, followed by short sudden increase of temperature, or vice versa, if there's long-term decrease of temperature, and then it is really, really, really important for the vegetation, right? So it's kind of obvious thing, but exactly no one actually showed this in data to show, yeah, if you're slowly increasing, that there is sudden increase in temperature, this will have severe consequences on the changes we see in the ecosystem, right? And this is, I think, for example, relevant to this question. We say, oh, we know there's increase in temperature, but we need to be worried to sudden increases because this has the biggest effect, right? For example.
So we don't know about the effects of the levels, but we care about it, right?
Yeah.
And so what matters is the change, right?
Both potentially, but this is the both mostly can get. Right?
But he showed it at longer temporal scale than the vegetation maximum.
No, it was.
No,
I forget, but I think it was like 20,000 years. Yeah.
And maybe one just a small question about the human and impact question. So you said that we have, let's say, two main sources. This archaeological data and then the pollen fossils related to food. Do we know how these two databases match? Or
so there was a talk here at the CTS, right? I forget when, but it showed that they are actually complementary, right? So the fossil pollen. So no, sorry, I'm kidding. So there is very little information about this. Not many people are actually using this. This is kind of, to my knowledge, this is kind of novel. I know, for example, Wojtek Abraham from Botany Department actually have been working on this, looking how these trends of humans from radiocarbon and pollen are correlated, and of course they differ at different scales, right? So they say for trees it could be the changes you see in a lake respond to area roughly with the artifacts of 50 kilometers around. But for her, it's even shorter, right? So there is some overlap. What is important is how far you look around the lake. And I think that we also discussed it with Honza Kolář, right? He was also talking here about this specifically. And it is very novel. Both of these are issues, right? That's the thing. But I think putting them together, both it's potentially very cool and powerful because they have issues, right? And we will never know. And there's of course lots of questions, right? You can say, you know, just a lot of humans maybe not important. What is maybe important is the increase of humans, right? Not suddenly there were more and they went down and cut down. If they already settled down, maybe their effect on big, right? There's also the question of, we know previously the humans have been moving quite a lot, right? And that's why it is important to look at, I think, a little bit bigger scales. And that's why the humans may seem kind of a lot, but it's because one group may came, live there 20 years, move past, another came, right? And they moved a lot around, but you are looking at 500 years blocks, right? So this will all show as humans have been there, right? So there are studies, but not on a bigger scale. So there is very localized, like for Czech Republic, I see. There are some from UK. And now in the project, we are actually using it globally for some of the components. And we found out, interestingly, for the patterns we are interested in with this, because we are looking at these big patterns of changes, like big changes in diversity, it is actually pretty far away. It's like the best area to look for the radiocarbon dates is around 200 kilometers actually. So but this is because we're going for the big changes, the sudden, you know, complete deforestation of area and this kind of thing. So but of course the local impact, right? And that's quite severe. But if you look at the general bigger impact, you need to sample kind of the case. Yeah.
Thank you for your great presentation. You have shown a nice figures about rates of change across continents. I was wondering, are these rates based on like changes in the species composition, or we can add more extra information?
Yeah. Yeah. So this is based on exactly species composition. So we look at. We have a core which has these levels, right? And we look how much species composition changed from one time to another. So it's beta diversity divided by the difference in time, right? And then we also, but because it's the difference in time, the time is very important, right? Because if the time getting very, like if they are very close to each other, the values will be just very high. So that's why there was a lot of issues with these matrices which caused that if in some particular period there were lots of samples, that there were just high rates of change values. And there was an issue, so I developed kind of ways around it. One of them is moving binning window, another is actually incorporating the uncertainties from these intervals, because you will say this level is 3,000 years old, but I would say this level is 3.5 to 9.2, and you can incorporate these, right? So this will be a lot of randomization, etc., probabilistic way, which determine, oh, this is actually the general trend of rate of change, right? So this is just composition based. Okay.
I just had a question still to this graph, to this picture, because I don't like it. But it's like related to your research. Why I don't like it? Because it's very conceptual and it has many assumptions, really many assumptions. And we tend to draw these pictures, and we are hypnotized by them, and we take them like a real reality, which is not the case, especially in this case. But I think your research is much broader. The ecosystem properties concept is affected not just by temperature. And if we talk about temperature, okay, with this assumption we can draw this picture. But if we talk about other properties or other drivers of ecosystem properties, we can draw very different graphs, pictures, and landscapes, or so to say, conceptual landscapes. And I think it's quite important because from your talk, it seems like you are fixed to temperature variables and so on. It's obviously not the case. So maybe, yeah, just the what would be for you the most important driver of this ecosystem property? How do you conceptualize the drivers in this research?
No. Okay. So this maybe this is the floating things. Floating things. Okay. So I agree with you. So sorry. Of course, this was just used from the paper. Here we have this. So I think your question, right? What we are trying to do, and this is a paper we are writing, is we want to compare these changes in these ecosystem properties, which is you can define, what is happening in the ecosystem for the last, let's say, 12,000 years, and to say, do we see that the changes are affected by the presence of humans or climate? And for climate, it's just not temperature. We have like 4 different climate, temperature variables. We have different growing season. We have precipitation, different precipitation values, and droughts, etc., and these kind of things. So the idea is that, of course, some of the changes we will see, and this will be very local, in some specific data set time, we will see that there is changes in lots of these, and this is important to remember. It's not just about diversity, it's the whole description of the whole ecosystem. Have we seen that it's affected by climatic variables or by our definition of the ecosystem? Right? That's kind of the goal, and I think it is a little bit in the path of these planetary boundaries, is to actually show humans have done anything in the past or not, right? And spoiler alert, if you look until the 2,000 years ago, humans have, even though we see some very localized impacts like Levant, where we know agriculture is for a very long time, etc. So there are quite differences in the variability of how humans have altered these. But in general, trying on a bigger scale, we don't see much impact of humans until very recently. And of course, we see climate changing depending, right? Of course, the Algerian transition, the climate was more important. And now, then during the whole scene, actually, it was much more important drivers on these ecosystem properties than presently. But that's okay.
So, any other question?
There were 2 beautiful pictures with the pollen. Did you generate them with artificial intelligence? Or?
Yes. So,
what was the problem?
I think that there are problems.
Yeah, sorry. The prompts are always there. I use Bing, which seems to be actually okay. For some of these,
That's at the beginning.
yeah.
Or the prompt is the tiny letters.
Yeah. Pollen sinking to the bottom of it.
Yeah, so pollen sinking to the bottom of the lake, comma, illustration, comma, digital art. For both of them.
Wow. I would imagine that you would need to much more detailed prompt for this.
No, Bing is actually pretty good at input illustration, digital art, or some presentation. Then it will just create these very, I think, good things. Of course, this is like nonsense, right? There are like stupid things, but in general, it's showing the thing you want to show, which I thought is much more better than me trying to draw a diagram.
So the digital art is also part of the prompt.
Yeah, so this is the whole prompt.
Okay.
So it's
interesting that you have to say that it should be art.
Yeah, because you can do
the genre.
Yeah, exactly. You have to specify, because you can do like Picasso drawing, or pencil drawing. If you do pencil drawing, you will have a very different thing. But if you do digital art, it will generally, to my experience. But of course, this is, you need to run it several times, and out of 20, let's say I pick these 2, right? Because you can just run the same prompts over and over again, or change it if you need. But I found it was understanding what I tried to do, and I just picked it. So there are more. I really like to use this in presentation because it is good to have some pictures that it's for free, right? And it's easy to do. So again, AI, I want to be optimistic. It's a great tool to do lots of things, and especially for this.
And speaking of this picture, I want to ask the particles of pollen. Do they get also decomposed somehow? Do you need special physical conditions for them to stay like they are, or are they so stable that they are not decomposing at all?
They are relatively stable, to my understanding. It is good that, of course, these sediments are oxygen-free, right, relatively compact. You also need the right kind of lake, which doesn't have massive changes to the bottom, right, because this will mess up your layers, but, better maybe, connect, but then you will take the samples and you will wash them in acid and these kind of things. So they are very stable, right? The things of extracting them from the soil, it's very crucial, like cool chemistry going through series of things until you have just the pollen grain. So they, to my understanding, are relatively stable. Yeah.
And why lakes? Because there is no wind, so they will sediment nicely. And
so you don't have to do lakes. Lakes just tends to be very good for this kind of thing. Lots of people do just soil. You can theoretically do just a soil or within a cave, right? That's an interesting thing to do, etc. Right? So it doesn't have to be, but in general, because of these sedimentation processes within these lakes, they have very good, these small, so you're much better. The resolution is pretty good. If you have good lake, just to be certain deep, blah, 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 then you have just a good results, right? It's much better. And that was the kind of, but also people do Myers and box, right? Which are also very good for these. Because again, it's building layers and layers and layers. That's what it is. Yes,
the stability just they are very stable chemically, but of course they are eaten by some bacteria like archaea, and so almost anything can be eaten, like plastics, for instance. Even today, the anthropocene plastics are all over around, and bacteria are already adapted to eat, like this is polyethylene and other plastics. So of course they are adapted to pollen, which is here for many million years. So you need just the conditions under which conditions that disable bacteria to eat the material, the sporopollenin, which is the oxidative process. So generally the lack of oxygen is the condition.
Lack of oxygen.
Because then the metabolic chain doesn't work at all. So that's the.
But in general, for any conservation, it's good to have like oxygen, right? So it's not surprising.
Organic conservation.
Okay. So if you mess up the layers, for example, in there will be some disturbance. Are you able to recognize it in the data that the layers are messed up? Or
to be honest, I'm not super skilled with this part of the whole process. I'm working with the data, but to my understanding, to find out this, because there is another process which we haven't talked about, and there's the age depth modeling, where you will have the samples of your pollen, but at certain intervals you also take another samples and you radiocarbon date those. Right? So if you find your radiocarbon dates are not matching, like going down, then you may detect, oh, there's probably sick or whatever. But maybe I don't know much about this like practical parts before the data is in the computer.
Well, it is, yeah.
Maybe we can look at it if there are no questions from the line.
Okay.
Jens, but otherwise,
Is there anyone?
I'm not sure.
I have one more question.
Okay, so let's
Indra.
No.
Is he asking?
No question.
No.
Hello to Srpsko. So one more question. We sometimes in modeling bird distributions, we model the ecological process where the birds are, but we also model the observation process because the birds can be detected with different probability in different time of year and different habitats, and so you have to kind of account for detectability, different detectability, so that you don't have biased data. do you also like account for this, because there will be probably different species will be detected with different probabilities, and different pollen will probably preserve differently than other pollen, you know, and these things.
So this is a great question. This is a big topic, and of course, I haven't talked about this. There are a lot of issues with pollen, right? So one of the issues is, for example, you only get pollen more or less who is distributed by wind, right? So you will not get most of the insect pollinated plants, right? Because they just don't produce that much pollen to be, because you need the wind to catch it up and then sink to the lake, right? So that's the one thing. Of course, there's another thing, which is that some trees just produce a lot, much more pollen than other trees. And there are, some people have done this, you have modern pollen traps on the lakes, and they will measure pollen traps. So they will have like a catchment area on the lake, and they will know exactly what's the composition of trees around it, and then they will compare it to what they found out in this pollen trap. Right, so you can, there is some information about the productivity of pollen in compared to this, and there's this whole big project called Reveals, which is using a lot of this information, also the size of the lake, etc. Right, but in general, lots of these are kind of like nothing. Like this is because it is, for example, for tropics, we just don't know anything about most of the taxa. Right? So lots of these things are known for Northern Hemisphere, or specifically Europe or North America, and that's the reason for that, because people have been doing this since like 50s or 60s, right? So there has been a lot of work being done, but in other parts of the world, the history is not so well established, and also people are not so willing to share the data yet, because in Europe most of these lakes have been cored, there have been published studies about it, so the authors are like, fine, take my data, whatever. But let's say in Latin America, there's a young researcher who will drill a core, and he's much less willing to make it publicly available until the person has some publication, right? So there is this bias, but therefore we know much more about these variants from, let's say, Europe and North America, but the species present there, right? And this is the pollen production, blah, 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 this kind of thing. But for tropics, we don't know it, right? This is kind of the issue. So lots of people, for example, like one of the things which we were interested in looking is, have we seen changes from trees to open landscape, right? This is very simple. We'll say, how much pollen are there tree pollen, and how much in a certain part was just non-tree pollen, right? And you will compare how this changed. In this case, we relate hopefully to humans, because you'll say if there's sudden decrease of trees, people probably cut those trees. But this is only possible to do in Northern Hemisphere, because for tropics, the same pollen grain, which could be genus or family, within the genus or family, that could be species who are huge 30-meter trees, but also this small elephants, right? So there are issues with the pollens we are aware. Some of them can be solved, some of them can't, right? But I always think it's an interesting like crystal ball, looking into crystal ball. It is still a crystal ball, but this is the best thing we have. And we don't have any better information now. And I think this is what I'm trying to do. Incorporating these uncertainties is important, and we should incorporate these uncertainties as much as possible, right? That's why I always try to do in the work that I'm doing is to incorporate this, like this uncertainty about the ages from the Asian model, we should include it, right? And there are lots of other things that should be included. It's not that we slowly should get better and better.
But yes, you are completely right. And statistically, the data, the pollen data are really weak, also statistically. So, because you always have some sampling effort in taking the samples, which is not really high, in fact. Although you have a sum of 500 or 1,000 grains per sample, it's still a quite weak effort, sampling effort. So, because you have, if you rank a complete database, if you rank the quantities through taxa, you have a very, very long tail, yeah. And if you look at this data statistically, so at the entire long tail is under the statistical criteria, like common criteria for robustness, yeah. So that's a problem. You know, you have only few taxa usually that are statistically okay, but the rest.
I agree, but there are ways to get around it. Of course, there's this. For example, it's important for diversity, right? Like rarefaction of random. You can do right to get better estimates of the diversity to have it to the same amount of pollen grains counted, for example. But also, I think, and that's why I said again, that's why I think pollen is very good for these broad strokes, like these big patterns, right? Because it is. Some people can do it, like be very detailed about their local site, what they're doing. But I think the strength of this is that there are some, we know, have them been trees, yes or no, like for Europe, we can find out from pollen grains. And that's a good information, right? That's better than we are able to do without it, right? That's why I think we are looking at these general big patterns, because I think if you go more nuanced, there are so many noise and issues that it will be very difficult to say, yes, this is how we are sure this is how it goes, right? Because of these uncertainties.
Or you can change in local scale, you can change approach, and then you use more indicator approach. If you find just one pollen grain of something that doesn't grow naturally in the region, it is brought by humans, so you can be sure that it's humans in there growing this exotic plant, for instance. So this is example of indicator approach, which is different, and so throughout scales, you change the project from this data-driven to indicator.
Yeah, exactly, right? And that's what we've been doing with the Northern Hemisphere project. Exactly, we were just looking for these specific indicators of plants which are not normally native there, because it was a small study.
Thank you.
Okay, so thank you, Ondřej.